All right, let's actually try out some support vector machines here. Fortunately, it's a lot easier to use than it is to understand. So I'm going to go back to the same example I used for k-means clustering, where I'm going to create some fabricated cluster data about ages and incomes of 100 random people. And if you want to go back to the k-means lecture, you can learn more about kind of the idea behind this code that generates the fake data. But one main difference here is that because I'm doing supervised learning this time around, I not only need the feature data back, but I also need the actual answers for my training data set. So what this function does is it creates a bunch of random data for people that are clustered around k points based on age and income, and it returns two arrays. The first array is the feature array that we're calling x, and then we have the array of the thing we're trying to predict for, which we're calling y, and it returns both of those things. And a lot of times in scikit-learn, when you're creating a model that you can predict from, those are the two inputs that it will take. A list of feature vectors and, the thing you're trying to predict that it can learn from. So we'll go ahead and run that. If you want to follow along with me, we're in the SVC IPython notebook. Okay. All right, so we're going to use that function to create 100 random people with 5 different clusters, and we will just create a scatter plot to illustrate those and see where they land up. So here's our data that we're playing with. And every time you run this, you're going to get a different set of clusters. So, I didn't actually use a random seed to make life interesting. There you go. And a couple of new things here. I'm using the fig size parameter on plot.figure to actually make a larger plot. So if you ever need to adjust the size in matplotlib, that's how you do it. And I'm using that same trick of using the color as the actual type, the classification number that I end up with. So the number of the cluster that I started with is being plotted as the color of these data points. And you can see this is a pretty challenging problem. I mean, there's definitely some intermingling of clusters here. So now we can use linear SVC. SVC is a form of SVM to actually partition that into clusters. So we're going to say svm.svc with a linear kernel with a C value of 1.0, it turns out. And C is just a error penalty term that you can adjust. It's one by default. Normally you won't want to mess with that, but again, if you're doing some sort of convergence on the right model using ensemble learning or train test, that's one of the things you can play with. And we will fit that model to our feature data and the actual classifications that we have for our training data set. So let's go ahead and run that and see what we come up with. Now, I don't want to get too much into how we're actually going to visualize the results here. Just take it on faith that this is a function that can plot the classification ranges in SVC. So if we want to actually visualize where different classifications come out, basically it's creating a mesh across the entire grid, and it will plot different classifications from the SVC model as different colors on that grid. And then we're going to plot our original data on top of that. So let's see how that works out. SVC is computationally expensive, so it takes a little bit long time to run. You can see it did its best here, given that it had to draw straight lines and polygonal shapes. It did a decent job of fitting to the data that we had. So it did miss a few here, missed a few in there, but by and large the results are pretty good. SVC is actually a very powerful technique. Again, its real strength is in higher dimensional feature data, but go ahead and play with it. By the way, if you want to not just visualize the results, you can use the predict function on the SVC model, just like on pretty much any model in scikit-learn, to pass in a feature array that you're interested in. So if I want to predict the classification for someone making $200,000 a year who is 40 years old, this would put them in our case, cluster number 1. And if I had someone making $50,000 a year who was 65, they would end up in cluster number 2. Whatever that represents in this example. So go ahead and play with it. Now, linear is just one of many kernels that you can use. Like I said, there are many different kernels you can use. One of them is a polynomial model, so you might want to play with that. So go ahead and look up the documentation. Good practice to getting you to actually looking at the docs. If you're going to be using scikit-learn in any sort of depth, there's a lot of different capabilities and options that you have available to you. So go look up scikit-learn online, find out what the other kernels are for the SVC method, and try them out. See if you actually get better results or not. Okay? So this is a little exercise, not just in playing with SVM and different kinds of SVC, but also in familiarizing yourself with how to learn more on your own about SVC. And honestly, a very important trait of any data scientist or engineer is going to be the ability to go and look up information yourself when you don't know the answers. So, I'm not being lazy by not telling you what those other kernels are. I want you to get used to the idea of having to look this stuff up on your own, because if you have to ask someone else about these things all the time, you're going to get really annoying really fast in a workplace, right? So go look that up, play around with it, see what you come up with. So that's SVM, SVC, very high-powered technique that you can use for classifying data in supervised learning. Now you know how it works and how to use it, so keep that in your bag of tricks.